So let us recall from the last lecture what we did last time. I want to recall quickly. So recall, what we did was we tried to analyze what happens to a matrix of a linear map when you change a basis. So let me write down the exact situation. VW finite dimensional vector spaces and we have V is a basis of V numbered by a finite set J. There is another basis V prime numbered by the same index set J, and also there is a basis W of Wi, basis of W, and W prime which is a basis of W. There are two. So these are basis of V and these are basis of W. And then each pair will give us a transition matrix. So transition matrix from V to V prime. This is the matrix, we denote it by M. V from V is the top index to V prime of the identity map of V, and this matrix I denote by B. Similarly, the transition matrix from a basis W to W prime. This is by definition the matrix from W to W prime of the identity matrix or identity map of W. This let us call it C, and both these matrices are invertible matrices. So this is in G L J K and this is G L I K. This we saw last time, and now I want to write down the relation between M V W F and M V prime W prime F. So this is equal to, this is I cross J matrix. So this is B inverse here and C here. Remember this I is C is I cross I matrix and B is J cross J matrix. So inverse is also J cross J matrix, and this makes sense because this columns is rows and this columns is rows, and this equality. This is what we have checked, the equality. And equality was very easy to check because I just put C equal to identity and then this was very easy to check. Okay. So before I go on to the definition, formal definition of the similar matrices, let me write one corollary. Now V is finite dimensional vector space, K vector space, and we have basis, one basis is V numbered by Vj, J in J, another is V prime which is Vj prime, J in J, and as usual B is a transition matrix. B is matrix of V to V prime of identity map. Then this is a transition matrix. Then the matrix of F with respect to a basis V prime to V prime F, this is B times M V V F B inverse. Just put in this C equal to B and V equal to W and W equal to V, basis W equal to V and basis W prime equal to basis V prime, and this is just a special case. So this allows us to give a following definition. Therefore, we define these matrices are similar, that means. So we define, last time in the last lecture, in the last few minutes I had goofed up little bit, so I wanted to correct it. So definition, now I write the definition purely in terms of matrices. Always I will follow the philosophy, whenever I want to define anything about matrices, first I will look into the linear map and their matrices with respect to the basis, and from there I get a clue what to define or what is worth to define. So let I be a finite set, and then we are looking at two square matrices, A and A prime belong to MIK. These are square matrices. These are also called I square matrices. Two of them then are called similar if there exists a matrix B which is invertible. There exists, allow me to change here, there exists an invertible matrix. B in, therefore it should be of the same order and it is in GLIK. Remember, this is a group under matrix multiplication, such that A prime equal to B, A, B prime. Then we call A and A prime to be similar. Now first important thing to note is the following. First important thing to note is similarity. So note that similarity is an equivalence relation on the set of I square matrices. That is on MIK, and therefore this set of matrices will be broken into the equivalence classes, and these equivalence classes I will keep calling similarity classes. So equivalence classes are called similarity classes. Of matrices. This is, it's really easy to prove it is similarity and equivalence relation, because clearly it is reflexive, symmetric, etc. That is because the GLI is a group. Okay. And what is the main aim? Main aim in the linear algebra, main aim of linear algebra is to give or to find simplest possible representatives for the similarity classes of matrices. That is in terms of linear operators now, in terms of linear operators, give a characterization of linear operators by using simplest possible matrices. So each similarity, the similarity class, if you know one matrix, then you know all the matrices, and you want to choose in each class the simplest possible one. That is the main aim of studying linear algebra, and all these, all the machinery is centered around studying this problem. And as we go on, I will make more and more stronger remarks about this statement, and this we will do it in the next chapter. And how will you do it? We are going to attach to a matrix or a linear operator a polynomial, and therefore we are attaching the zeros of that polynomial, and therefore we are attaching the multiplicities of that polynomial, and whether this data is enough to characterize them, that is a question. Okay. Another important operation on the matrices, another important operation on matrices is the following. So let us write it as a definition. For a matrix A, in I cross J matrix, MIJK, Ij finite sets, Ij finite, I define the matrix in the other order. So transpose matrix, transpose I write on the other side. I do not want to write on this side because you will confuse with the power. So this is, if this is Aij, I in I, J in J, I want a matrix which has the rows are numbered by J and columns are numbered by I. So this is Bji, where J in J, I in I. This Bji is nothing but Aij, J in J, I in I. This is called this matrix, the new matrix is called the transpose of A. Now various questions have cropped up. What happens? Many invariants like rank, nullity and so on about the transpose and this and that. Okay. So jth column of the transpose or ith column. Ith column of the transpose is the ith row of original matrix, and jth row of transpose is the jth column of A. Rows and columns are interchanged. So it is basically like taking a reflection around the main diagonal, roughly speaking. So the unit matrix or identity matrix we have denoted by E suffix I. This is the matrix delta ij, ij are in I. This is either called unit matrix or the identity matrix. Matrix in MI. We have seen that this MIK is a K algebra, and this identity unit matrix is the identity in this K algebra with respect to the multiplication of matrices, and the transpose of this unit matrix is itself. Moreover, we have the following computational rules. Moreover, we have the following computational rules. Okay, so all these are now in this A and A prime are two matrices of the same order I comma j, and B is a matrix in the number the row numbers are given by the j and column numbers are indexed by the set R, and A is a scalar. Then first of all the transpose of A and again the transpose of this, you get back the original matrix. Second, if I add A and A prime, addition is possible because they have the same orders, and then take the transpose, that is same as transpose of A plus transpose of A prime. This means the addition of matrices respect the transpose. Third one, if I multiply matrix A by scalar A and then take the transpose, this means it is same as A times small a times the transpose A. And the fourth one, transpose of A times B. Note A and B are not the same order matrices, but the product makes sense because of our assumption on B that B has the rows of B are numbered by the same as numbered by the columns of A, and this is same as first you take the transpose of B then multiply by transpose of A. This product also makes sense because the rows and columns get interchanged. So these rules are very easy to verify. I will not verify them, but I will note the following important thing. Note that the map from square matrices I cross I to square matrices again, this is a K algebra, this is a K algebra, and I am giving a map from this K algebra to that K algebra, so that is A going to transpose of A. So it shows that this map is K linear first, that is the property second and third, and so if you call this as a I don't want to give a name. So this map is K linear, and the fourth says that it does not respect the multiplication but it reverses. So it is Sometimes it is also called anti-homomorphism. Anti-homomorphism. This refers to the term multiplication operation. Anti-homomorphism of K algebras. And more than that, it is involution. That means square of that is identity. So that means it is self inverse. So this means a map is called involution when F square is identity. So it's self inverse. So that is also called self inverse. So these are their properties. So sometimes it is useful. Lot of such anti-homomorphisms come in actually study of cryptography H. Okay. So that was about this. Now the immediate corollary, another observation from these rules are, I want to write it as a corollary. So corollary, again I is a finite set, and then we want to say something about this group. So A is an element in the group GLIK. That means A is invertible matrix. So that is A is invertible in MIK. It is an invertible element in the K algebra MIK. Okay, then on one hand you take the transpose first and then the inverse. Note that if A is invertible, the transpose is also invertible. That will follow from one of these rules. You see, if A is invertible, there is a matrix B, so that this AB is identity, and the transpose of that will be the other way. So that means this inverse is nothing but first you take the inverse and then take the transposition. These two operations are commutative. So inverse and transpose, they are commutative operations. They reverse. Okay. This is again very simple to check from these rules. So I will not write a formal proof. Okay. So sometimes this matrix, this transpose, A transpose inverse. So I would have, without loss I will denote this without putting a bracket, because whichever I do it first, it is the same. So this is same as either you take it transpose A inverse or you take it transpose of A inverse. This we have checked, it is same. So this matrix is called contra gradient matrix. Contra gradient matrix of A. This concept is defined only for invertible matrices, and this is very useful in physics. When I do a geometric part, that time I will show you the use of this contra gradient matrix. Okay, now the next I want to analyze the following. If you have a linear map, so next problem I want to analyze is, if you have a linear map from V to W, F, then we know the dual F W star to V star. There is a dual map F star. Recall how did we define dual map? That means we should know where the form on phi linear form on W. That means it's a map from K linear map from W to K. Where does it get associated under F star? So F star of phi should be a linear form on V. So that it should be map from V to K. And which map? F star V, F star of phi is F composed with phi. makes sense. First you follow V to W, that is F, and then W to K by phi. So this is a definition of the star map. This is called a dual map of F star, F of F, denoted by F star. F star is called a dual map. So now the problem is, we know that if I have given a basis V, Vj of basis of V, and basis W, Wi, I in I of W. We are assuming both finite dimensional, so I, J finite sets. And then this basis will give a dual basis. So V will give a dual basis V star, which is Vj star, J in J. This is a dual basis of V star with respect to the basis V, and similarly I will get a W star. This is W star. These are the coordinate functions of the basis. So this is a basis of dual basis of V with respect to the basis W. And now on one hand we have a matrix of F with respect to this basis. So M V W F. On the other hand we have this matrix M. Now you have to be careful. Upper you have to write W star, V star of F star, and obviously we are asking the relation between the two. Right? See the strategy when you write these indices in this notation matrix of F, the top one coming from where the map is defined, and down one is where the map is going into. So the relation is, one is the transpose of the other. So this M W star V star F star, this is nothing but the transpose of the matrix M V W F. Proof is very easy to check. Let us write down the proof. Remember the matrices, this matrix of F with respect to the basis is defined by these equations J in J, F of Vj equal to summation Aij Wi, I is in I, and these coefficients define the matrix M V W F is by definition then the matrix Aij, I in I, J in J. This is in Mi Kj. So if you want to get the description for this matrix or ijth entry of this matrix, then we have to evaluate F star on the dual basis. So we need to find a formula for F star of, now the orders are interchanged, rows have become columns. So F star of W I star, we have to find out this. So for a given I in I, we want to find this formula in terms of Vj star, and those coefficients will give the ijth entry of jith entry of this matrix. So this is, now these are what? Where is this element? This element is a linear form. This is in V star, because F star is a map, linear map from W star to V star, and Wi star are the coordinate functions here. So when I go under F star, it will be somebody in V star. So therefore I will have to evaluate, to understand this, I will have to evaluate, or when directly write this, I have to write this as a coefficients. This I want to write in terms of the basis j in j, b j I v j star, and the matrix with this equations, the matrix of f star with respect to this required matrix is nothing but b j I, j in j, I in I, and we need to verify now what? We need to verify that bji is aij. So, we need to check bji equal to aij for all I in I and j in j. Okay, fine. So, let us let me write that equation again. We have written this equation and we want to calculate bji. Oh. Both are linear forms on V. This equation is in V star. So, I will evaluate to check the equality, means they are equal on every element of the basis of V. So, I evaluate this on Vj, f star of wi star evaluated at Vj. This should be also this other side, j in j, bji vj star. Oh, I have, okay, evaluated, and this whole thing I should have taken some other index. Okay, let me write the index. Okay, write the index k somewhere. This is k and this is evaluated at Vk. So, the only term which will survive in this sum is j equal to k term. They are the coordinate functions. So, j equal to k term will survive, that means this is bki on this side. On the other side, what is the definition of this? That is, the definition of this is a composition, right. This is a composition wi star f evaluated at Vk. Which is wi star of f of Vk. But this is now Vk we have written, f of Vk we have written, this is wi star of Vk we have written as summation I in I, a I j, no Vk. So, a I k wi. This is this I have written. This is, now when I put this again, so only term which will survive is I term. So, this will survive is aik. So, therefore, we have proved bki is equal to aik. This is true for every k in j and for every I in I. So, that check this condition. So, therefore, we have checked that the two matrices are equal. We will take a short break and then come back.